Okay, let's start. Today we'll talk about compression bounds. And stability. So let me remind you what we're doing. So in this class, the goal is to, in this part of the course, the goal is to expose you to as many ways as we can to proving generalization bounds, to understanding why a learning algorithm can take data and can output a hypothesis, f hat, such that it does well on unseen data. Last lecture, we looked at a particular bias variance decomposition, which was very different from the usual constrain yourself to a class F type of decomposition. And that bias variance decomposition was giving us results for local methods, a provable performance on out of sample performance on for local methods that do some kind of averaging of the y variables in the neighborhood, much like a k-nearest neighbor type of methods. But we didn't have to go through uniform deviations. We didn't have to go through any kind of machinery that we went through before, like Rademacher averages and things like that, right? So it was a very different analysis. In some sense, there were no parameters other than that bandwidth h in the Nadaraya-Watson estimator. There were no really no other parameters. In fact, one calls this a non-parametric method because you can think of having one parameter per data point. You put as many bumps as you have data points. So as you can think of this as many parameters as data points if you wish, right? So again, in the context of what is the complexity, what is the real number of parameters, it's really hard to say, right? Here we have a successful method, Nadaraya-Watson, with just a single bandwidth choice, and it's non-parametric. There are as many parameters as data points if you wish, okay? So we have to keep this in mind as we go forward when we talk about neural networks, in that the number of parameters is not the right measure, maybe. Even the size, the norm, maybe is not the right measure. It's really subtle how you measure complexity of a model. Now, the two methods that I will describe today are, again, algorithm-centric, in the sense that we don't split the bias variance according to some class F. We are proposing an algorithm, and then we're studying that algorithm. So rather than studying very abstractly bias and variance for any method that outputs a hypothesis in the class of F of functions, we're going to assume that there is some algorithm F. We denote it by f hat n, and we want to understand its expected loss. Remember that this is a expected over a pair xy, L of f hat n at x, comma y. This is the expected loss on the new data point, drawn from the same distribution, and we're looking at the object of interest is the expected LF hat n. Now, when we started studying this object, this is the quantity of interest, how well we learn, we looked at the empirical risk minimization algorithms, and for those algorithms, we boiled down the difference between the best in class f to understanding the L of f hat n minus L hat of f hat n. Okay, this was a three-term decomposition. One term dropped out, one term became 0 in expectation, and so this was the upper bound. Now, sometimes people argue that this is the object of interest, and so this is what we're going to study. This object in itself is interesting because it says, can I relate my out-of-sample performance for my method to the empirical values, to the empirical fit on the data for that algorithm, right? So in general, we saw that this is a biased, this is not 0, right? This is a biased difference. This is a positive, typically, difference because the f hat n depends on the data on which this is evaluated, right? Everyone is fine with that, right? So sometimes people call this a generalization error. Sometimes people call this the generalization error, the expected loss. So you have to be careful. Sometimes it's just this, sometimes it's the difference, and really differs from person to person, right? Let's call this a generalization gap, right? So this is you train a neural network, you evaluate it on the training data, it's close to 0, and then the question is, can this be close to that, right? So what are the different techniques for this being close to that? Remember, the issue, again, was that this f hat n was computed on the data by minimizing empirical risk, and this is the value of that empirical risk. So f hat n depends on the data, and it's being evaluated on the data. So if we didn't have the hat on both of them, then this would be the central limit theorem, right? Everyone is okay with that? This would be the average of random variables whose expectation is this, if we didn't have the hat on the f. So it's somehow dependence of f on the data that is problematic. And what these two methods will do is they will limit this dependence. That's all we're going to do. We're going to say that we're going to assume that the algorithm, fix an algorithm, we're going to assume that it has limited dependence on the data. In particular, for compression bounds, we're going to say that f hat n depends only on k, on a subset of k data points. Okay, that's a statement that I will make precise. And the stability approach will say that f hat n does not depend too much on any one data point. And here I mean the training data point. Okay? So these are the two approaches. They're kind of similar, but the assumptions that they make are different. And we'll spend 15 minutes on the first one and then an hour on the second one. Okay? Sounds good? Now, if in this example I say k is equal to 0, that's great. The algorithm doesn't depend on any data. If it doesn't depend on any data, then of course you can remove the hat, right? The same thing for the stability approach. If f hat really doesn't depend on any of the data points being removed, well, you can consider a constant algorithm that just doesn't look at the data and outputs a single function. it's just not an interesting algorithm, right? So again, you can see that both of them in the limit, they can give you that this is small, this difference is small, but it's not an interesting algorithm. So there are two parts to this story. One is, do we know interesting algorithms that actually have these properties? And two, if you assume these properties, can you show that the generalization gap is small, right? So there are two parts to the story. And I'll try to show both. All right, so part one, the compression bounds approach. So what I want to say is the following, and it's really easy to describe, and I'll formalize it in a second. So suppose that the data set S is, now I'm just going to write it as a Z1 through Zn. Remember that the Zi is just a pair xi, yi. And I'm really abstracting this away. There's a, I don't need to talk about a specific loss function. This will work in generality. So there is some loss function, and if I compose the loss function with f, then let me call that g. So to each f, there corresponds a g. And so I'm going to be working with L composed with f hat n is just going to be g hat n. What I want to say is that given the this set Z1 through Zn, this function g hat n will only depend on the subset of these data. That's what I want to say. So what are the examples? So suppose you've got, it's kind of a silly example. So you've got rectangles, and you know that, again, this is really a toy example, just for illustration. And you know that there exists some rectangle such that everything inside is labeled as -1, and everything outside is labeled as a +1, right? Now you can have a lot of data, but when you do minimization of risk, when you're trying to fit a rectangle to the data, you really only depend on 4 points. These are the 4 points inside the left, right, the bottom left, and so forth, right? There are 4 points that define this rectangle. So this has a kind of a compression of size 4, right? Yes?
So this is sort of a local statement, right? Because if you move something that's right in the middle very far away, then it can become the new left.
So the claim is that if there exists a rectangle that labeled everything inside with minus and outside with plus, now you forget about this rectangle and you just look at the data. You come up with some other solution, but if you removed all the points except for those 4, you would still come up with the same solution.
Right. I see. Mm-hmm. When I say it's local, I mean like you would get a different solution if you drastically changed one of the points, which was not one of those 4 points.
That's right. So if
so it's sort of only locally robust to
that's right.
small variations.
That's right. That's right. So the stability approach is going to be more, I think, what you're saying, like perturbation of a data point. This one is more like a compression. Can I take my data set and compress it to a small subset, right? So there are different formulations of compression. Let me just say that there are different formulations. I will present a simple one, and then you can read, the kind of the more complicated ones where you have a compression function, reconstruction function, and so forth. So this is what I want to say. There exists, this is assumption. The assumption is that there exists some, choice function that when you give it a data set of size n, it returns a subset of subset of z1 through zn, and the size, the cardinality of the set is always bounded by k. Okay, that's what I want to say.
What is C? So
C is some choice function. So I'm assuming that there exists a choice function.
this is a compression function.
This is a compression function, right? Let's put a subscript k on it. That can always, for any data set, it can choose a subset, right? Now, I haven't said anything, okay? I'm just saying that there exists some function that chooses a subset. But what I want is that a g hat n. Now I have to really write out that g hat n was trained on n data points, and I want to write out which ones they are, right? So, of course, it's a function, but the way that I got this function was to look at z1 through zn, right? So I'm going to use this notation throughout the lecture, but still keep in mind that this is a function, so I can evaluate it at some z, right?
You could use the subscript Sn.
I could use a subscript s, yes, okay. Yeah, I mean, I can replace it. Is that what you meant? Right, so what I want to say is that this function is equal to, okay, let me follow the suggestion. S is the same as g hat k of ck of s. So in other words, if I just said, I don't have this huge data set, I only have this subset, and I output the hypothesis. Okay, this is a loss of the hypothesis, but you get the idea. That's going to be the same as the original one, right? Does that make sense? So if I erase everything other than the four corners, I will output the same rectangle. Yes?
Do you have any requirements? So your only requirement of C is its size is smaller than K. Do you have any other requirements such as like this selection will preserve your boundary or something like the zero boundary like in that case? It's not true that you can pick any 4 points. You have to pick the kind of corner points.
Well, this is the that's what it means, right? So there is a okay. Now there's a kind of a choice, right? You can choose this rectangle. So I'm assuming that the algorithm will pick like the minimal one, or some midpoint. There is some way to break the ambiguity. Okay. Again, this is a slightly simplified version. The more complicated one would say the g hat k is not the same function, but it agrees with the original function on the training data. That's all I need. I don't actually need it to, as you'll see from the proof, I don't actually need these functions to agree everywhere other than the data. Okay?
The data mean like the whole endpoints?
Second, sorry?
The whole endpoints of the data?
Yes, on all endpoints, yes. Okay? So the claim is that because now this algorithm weakly depends on the data, right? So think of like support vector machines being compressed to just the supporting vectors, or the hyperplane being compressed to just defining vectors, right? So the claim is that this is enough to guarantee that this generalization gap is small, right? Because it's mostly independent if k is small. Questions? All right, so let's try. So I'm going to write expected, this is the generalization gap, L of f hat n minus L hat f hat n let me just write it as expected over the data set S of G S. Okay, so expected over Z G hat n of Z minus 1 over n sum of G hat n of Zi I from 1 to n. And let me make this, again, this explicit, that this is a function of the data set, and then I'm evaluating it at Zi. Okay, so I just wrote, so I don't have to write loss of f, I just wrote it like that. Okay, this is just our convention. But now I'm going to use this. So I'm just going to plug this in. Right? So if I plug this in, I get expected over the data set, expected over Z, G hat n of Z, minus 1 over n sum I from 1 to n, G hat n, G hat k, sorry, of C k of S evaluated at Zi. Right? And so you see here, to make this step, in fact, I don't need these functions to be the same. I just need them to be the same on the data. Right? So maybe I can write it directly. Zi is equal to Zi for any I in the data set. Okay? Question?
Yeah, what's the difference of G hat and Z and G hat and S Z? So
What's the difference between
G hat and Z, this one and yeah, and the G
this
hat
one?
and S, yeah.
It's the same. Here I just made it more explicit.
Okay.
Yeah. So G hat n is always a function of S implicitly,
So
right?
they are equivalent.
It's the same, right? Questions? Okay, so you see this function gk hat now takes a subset of the data, but it's being evaluated on all the data. That's what we're gonna use. That's what we want to use, right? It only depends. This hat only depends on a subset of k points, and for the rest, it's really like out of sample. So it's only in sample for k points and out of sample for n minus k points. That's all we need to use, right? Okay, so but how we do it? How do we make it precise? So one problem is that there are the subset is chosen based on the data itself, and that's a problem. So we can't just say it depends on the first k. You know, who knows? It could depend on some arbitrary subset. So when we want to bound deviations in a kind of in a way where we don't know which function or which subset is chosen, what's the trick that we use? Just take a max over it, right? Just take the worst, because whatever we're gonna pick is contained in the worst one, right? So this is upper bounded by expected over set S, max subset of, so let's say I is a subset of n, and the cardinality of I is bounded by k, okay? All right, and now we're looking at the expected g hat n of Z I need to make this? Let's see. Yeah, I'm going to make the same substitution here so I can do it at the same time. So here we have expected over z, g hat k of ck of s evaluated at z, right? It's what was asked, right? Is this the same as this? Yes, this is the same function, right? Now let's make let's take the maximum. So now this is a expected g hat k, and I'm going to use the notation s sub I to denote the subset. S sub I is the subset of I. Okay, yeah, you're right. You're right. So okay, this was the reason. Good. So let's make it the same function. Thank you. I remember there was a reason for this. There is a different version of this where you don't have to make this assumption. Okay, I apologize for that. So these functions are equal. Yes.
So the function must depend on the data.
The functions are equal everywhere on z. Okay? I just rewrote with a different notation, and I'm taking the max over Si. So Si is just Si is the set of Zi where I is in the index set I. Okay? Yes.
I is the set of indices that comes out of C sub k of s, right?
Yes, exactly right. So this is a data-dependent choice, and now we're getting rid of that data dependence by taking the maximum. Right. So once S is drawn, ck of s is a particular choice, so we can just put a max after the expectation, right? It's exactly the same idea that we had for empirical risk minimization. At some point you're saying, well, I don't know where this f hat is, so let's remove the hat. That removal of the hat is exactly this step, right? Okay, I mean, the notation is a bit cumbersome because we have to write these things out. But I hope you can actually feel it. Like, you almost feel it, right? Like, this is... Like, this really depends on only k data points. I mean, take one data point, right? If the algorithm only looks at one data point, and it would be the same result if you gave this one data point, then for the rest of the points it should be like out of sample, right? You can almost feel it, but okay, to make it precise is a little bit more cumbersome. By the way, when we get to stability, we're going to be writing very much the same type of statements. So now, of course, this sum is over what's in I and what's outside of I. What's in I is problematic. What's outside of I are unbiased estimate of this. Yes? So let's just get rid of, from the sum, let's get rid of those k guys. Let's remove them and replace them with another draw. Right? Let's see, what's the easiest way to write it? Let me just leave it for as a homework. I mean, at this point, it should be simple enough, right? K of these guys are problematic, right? If you replace them with k other guys, right, then you can do it because in expectation you're not paying for that, right? Yeah, this is a good exercise. So let me do that. This is going to be a homework. By the way, I think I'm going to need 1 or 2 more days for the homework. But hopefully today we'll find enough problems for you. Okay. Of expected g hat k of s I of z minus 1 over n sum over s. It's harder to write this. Okay. So a set, let's call it s prime, and then g hat k of s I at zi, where zi now belongs to si. Sorry, zi belongs to s prime. And so how much did we lose? Well, the functions are bounded. Assuming the functions are bounded, by the substitution, we just lost k over n times the range of the functions, right? So something like at most, yes, at most k over n times let's say b minus a. Maybe there's a factor of 2, so something like this, right? Where the loss function is bounded between a and b.
So the loss function cannot be the square.
For square, you would need to make sure that the functions have finite range and right. So let's say g is between a and b. So is this step clear? Now, what is s prime? So s prime is s, where you subtract it off the problematic set, and then you put in a new subset, s prime I, right, of independent random variables, right? So you took out the bad guys, put in a replacement, which is an IID draw. Yes.
What's the expected button? Right.
Second?
Or I guess this is an expectation, but I don't really get why you can't be left to give this inside the map. Like, what if you have to draw ones that are even better than?
Yeah. So this is an expectation. It's going to be an expectation. Yes. And this expectation will have to be over both. Yeah. This is an exercise. It's good exercise. Okay. Good. Right. Okay. But this is a zero mean random variable now, with fluctuations with variance of order 1 over n, or standard deviation is 1 over square root of n. And we know that the max of, whatever number of these guys is bounded by square root of log of the cardinality of the number of them, right? So this is, at the end of the day, this is going to be bounded up to a constant that I'm going to skip by square root of log cardinality of how many subset of size k are there. Well, it's just n choose k over n. And there is some constant here. Plus k over n times the range of functions, b minus a. Again, some constant. Okay? What's the behavior of this? Well, it's square root of k log n over n. Right? This is order k log n over n. Now, the size of the compression set is k, but this looks very much like the VC dimension bound, right? VC dimension bound was square root of, well, I guess we never wrote down the VC dimension, but a VC dimension bound would be something like square root of VC dimension by n. So up to log factors, it's very similar. In fact, let me give you an example. So suppose that we look at thresholds. Thresholds. So the data is, let's say, plus, minus, plus, minus, 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 plus, minus, plus. Okay, whatever. And you're looking for a threshold that best separates the data. Okay. Now the threshold is going to be somewhere between 2 points, and let's just agree that it's going to be a midpoint of 2 data points. And it will have to have the property that, let's say, the plus is on this side and minus is on this side, because otherwise you can improve the empirical fit to data. Now, I can throw all the points but 2, and I get the same result. So k is equal to 2. So learnability of thresholds is you get square root of log n over n. Right? Of course, the true one is, well, that's exactly the result we got, remember, for the Kolmogorov type of quick back-of-the-envelope result through Rademacher complexity. But this is a different approach, right, based on compression. So up to log factors, this is correct. Well, so how many sets of size k are there out of n? Yeah. No?
But why graph on max to?
So, right. So I'm using the result that says that if you've got a collection of let's say sub-Gaussian random variables, then its expected max S in some set S. Okay, I don't want to use S, sorry. Let's say N. And N is a finite set. Then the maximum behaves like square root of 2 log cardinality of N. And then there is the standard deviation of these variables, which is 1 over square root of n for us. Other questions? Yes?
What's that theorem that you just wrote?
That theorem?
What you just had.
What I just said is a maximum of, it's the expected maximum of n random variables.
Right, what's this called? Is there a
Is there a name? I don't think there is a specific name, but I can give reference why this is true. So it's a session, and just take it as a given. But I mean, you can even simulate it in the computer. So draw a Gaussian and draw a bunch of them, and now look at the maximum, and then plot how the maximum behaves. And you'll see that it grows like square root of log n.
Does it need to be a Gaussian or can it work for
Sub-Gaussian is okay. So sub-Gaussian means that it need not have tails like that, like a Gaussian, but the tails should be smaller than the Gaussian. So in particular, a bounded random variable is always sub-Gaussian, because you can think of this as a box, and you can always put a Gaussian on top, right? So you dominate the tails. So a bounded variable is always sub-Gaussian. Yes?
Here we are considering the cardinality of I to be less than or equal to k, right? So there
Yeah.
are much more elements than n choose k.
Yeah, but not too much more, right? The n choose k is the dominating one. You're right. You're right. I need to be more careful. But the order is correct. Let me make this C bigger. Now it's correct. Okay, so yeah, so let me give you a hint of how to do this. If I ask you for the homework, you need to come up with the extra. You need to add and subtract the fresh samples for that bad subset, right? And the way that you're gonna do it is you're gonna write it as an expected version, and then pull expectation out. Okay, that's the way we're gonna do it. So this expectation is gonna be over S, and whatever the replacement is, let's say S prime. So S prime is a Z1 prime, Zn prime. Any other questions? It's pretty simple, only 4 lines, right? Yes.
So we showed in Rademacher average that we can like condition on data sets. So
Yes.
is it that the reason that we like assume that it only depends on k data points and do not use that is that it's hard to compute the average, or is like because it's similar bound like there we also like show that like there is a theta and like it shows that basically that set is finite, something similar.
Yeah. So one could get an interpretation. There was a paper 10 years ago showing that there is an interpretation of this as through Rademacher averages. The problem is that the subset is data dependent because you're looking at all these the choices of I after looking at the data. So now you have to get rid of that dependence by doing the max, and that gives rise to some Rademacher average type of behavior. Yes. So there is a connection. But I want to stress that we never looked at any capacity here, right? Any complexity of a class. The kind of the worst thing was this maximum over all subsets of the data. It's really algorithm-centric analysis, right? We look at the algorithm, and if it happens that it has this compression type of behavior, you get the result, right? So homework, prove this, and prove that for neural networks you have a small compression set. No, that doesn't. then that could go straight to the publication. I don't know. So I don't know of analysis that would say that for neural networks there's a small compression set, and it's probably not true, right? I mean, we don't even understand how optimization works, right? So you can only do it on toy examples, maybe. Okay, so I'm not saying this approach will work always, but there are situations where it's simple enough. It's good to keep in mind when you think about limiting this dependence. Again, I want to stress that what we're doing is we're looking at the difference expected L of f hat n minus L hat of f hat n. And if we show that this is smaller than square root of k log n over n, this result is only interesting if this is small, right? If you have an algorithm that doesn't actually minimize empirical fit to data in some way, then this is a useless result, right? So the algorithm has to have this compression property, and it has to have this minimization property on the data, right?
So
minimizing the empirical.
Is this going one way? So if you have a compression, you have generalization in that sense.
Mm-hmm.
Does it go the other way? So if you have generalization, no.
No, I mean I can come up with all kinds of okay. You have so we have to be careful exactly what the setup is. So let me just mention that 15 years ago there was an open problem whether existence of a small compression scheme, such as size k compression scheme, in a bit more general setup where you have a compression function and a reconstruction function, close to this but slightly different, whether existence of a compression scheme is equivalent to VC dimension. So what one can show is that if you have a compression scheme, then you have a finite VC dimension of the effective class. Okay, if the algorithm is working with some class and it has a compression scheme, then there is the VC dimension is finite. The other way is still an open question, though in the last few years there has been some progress on this question. I wouldn't advise looking at this problem. I've spent a few months of my life without any progress. So the open question is to show that if a function class has a finite VC dimension, then it has to have a compression scheme of size, order of VC dimension. Yes?
Can k be a function of n, such as like square root of?
Yes, nothing here prevents that, as long as it's...
Sorry, what was the question?
The question is whether this k can scale with n, and the answer is yes. It's just you lose the rate, right? You're going to get some slower with n sample complexity. Let me also mention that one can use, instead of kind of this simple expected max bound, one can use what's called the Bernstein inequality. Maybe we should do that for the homework as well, where you should be able to get a 1 over n type of behavior rather than 1 over square root of n. Or instead of square root of k over n, to get k over n behavior. Okay? In some situations. Okay. All right, so now...
there are a couple of pages in Vapnik's book in which there is a somewhat qualitative, I don't think it's very formal, but argument that if you have a learning algorithm, you can compress.
Yeah, I don't know. I mean,
the intuition is that you can predict.
Yes. So there's definitely a connection between prediction and compression.
Yeah.
In fact, once you work with log loss in information theory, these become really the same problem. Whether you have a compression, like a lamp-LZ for your file, or whether you can predict with this method, right? These are really dual to each other.
But
But in general, I don't know
tell you
what
something about this question, not really, right?
Yeah.
Okay.
Okay, so now what I want to do is I want to replace this by something else. and it will have the stability type of feel to it. So what is stability? Stability says that your learning algorithm shouldn't change too much when you perturb one data point. And now I have to tell you what it means to not change too much, what it means to perturb a point. Is it an expectation? Is it the worst case point? Do I remove it or do I replace it with something else? All kinds of things like that. And for those who have been studying differential privacy, this has the same feel. The output of a randomized method, our methods are deterministic, but you can consider randomized as well, should not change too much upon inclusion or exclusion of a particular person from a database. That gives some kind of privacy or illusion of privacy, I should say. All right, so what I'm going to do now is I'm going to, again, write this as a bit shorter, so we don't have to have the loss function there. This is the expectation over a data set of the expected over z g hat n of z1 zn with square brackets evaluated at z minus empirical g hat n of z1 through zn evaluated at zi. Now, I believe we've done this before. If I look at just the second term, the expected over a data set of 1 over n sum of g hat n z1 through zn evaluated at zi. If I push the expectation inside, and if the algorithm is symmetric, so what is symmetric? It means that it just looks at a batch of data. It doesn't care about the ordering of the data, right? So if I gave it a permutation of the data, it would output the same thing, right? Which is not true for the stochastic gradient descent, for instance, right? But suppose that the algorithm is symmetric, then this is equal to expected over a data set. They're all going to be the same, g hat n z1 through zn at z. Now I can put any index here because they're all the same. So let me put 1. Right? Once I push the expectation inside, all these terms are the same. So I can just pick one of them. So let's say this is z1. So what is the difference of this first term and the second term? So this is an aside, right? Let's have it as how. Let me continue this equality here. This is just an aside. This difference now becomes, I'm going to use linearity of expectation. Can everyone see here? All right. And z. G hat n z1 zn at z minus g hat n z1 zn zi. Okay? Let me decode this for you. What this is saying is take n plus 1 data points at random. N points and 1 more. Train on n points and test on n plus 1. Or train on n points and test on the first one, or the, let's say the first one. Doesn't matter which one. That difference in expectation is exactly the generalization gap in expectation. It's exactly the notion of in-sample versus out-of-sample. You're looking at out-of-sample performance minus the in-sample performance. And now is going to be the most mind-boggling step of the whole semester. No, it's not that bad. You see, these are dummy variables. You know, if I were to write this out, this would be n+1 different integrals. They're all dummy variables. I can take any name and replace it with any other name. So let me take first the expectation of this guy. So by linearity of expectation, I'm going to take expectation of this guy and expectation of this guy. When I take the expectation of this guy, I'm going to rename Z and Z1. Z and Z1. And then I'm going to, again, combine them by linearity of expectation. So that is going to be equal to expected S and Z, G hat N of. Okay, so Z1 got replaced by Z. Now I got Z2 up to Zn. And now I evaluate at Z1. Now this is still out of sample, right? Because I trained on these guys and tested on Z1. The Z1 was never in my data set now, right? I just renamed. Or did I want to do it to the last guy? Maybe I wanted to do it to the last guy. Again, it doesn't matter. Let's see what I did in the notes. So I want to add Z1. Okay, fine. Let's do it like this. And let's keep the other guy the same. Z1, Z, N. Does that make sense? So we're testing at the same point now, unlike this, right? This was testing at different points. One was in sample, one was out of sample. Now we're testing at the same point, but again, here it wasn't in the sample, and here it is in the sample, right? Just renaming, right? So I hope that most of you just say it's trivial. It is trivial. But it's some kind of notion of stability, right? It's some kind of notion of stability which says that the output of the algorithm, or in fact the loss of the algorithm, shouldn't change too much when I replace one point with some other point, right? Okay? You can call this notion some stability. I think we had some name for it. Forgot the name. It's been a long time. But okay, it's a notion of stability.
Cross-validation.
Now I forget. Yeah, it doesn't matter. So everything is equality. So you see that stability is necessary and sufficient. It's equal. This notion of stability is equal to the generalization gap. Yes. Yes.
Here, it's slightly different because we are comparing the fact that we are comparing two expectations when one of them is in the data set and one of them is outside the data set. So, if, for example, if there is an algorithm that makes the error and the data point
Yeah. So.
It's like,
So differential
it's kind of
privacy.
different than differential privacy.
It's a bit different, right? So I want to say that the other notions of stability or privacy are stronger than this one. This is the weakest you can find because it's all equality. And now the stronger you make it, the better things you can prove, essentially. And differential privacy, which actually is with respect to a randomized algorithm, not with respect to a deterministic. This one is deterministic. We'll do it on Monday. Is another way of doing it, as a stronger notion for doing exactly the same. Okay. So in particular, I can upper bound this by some stronger notion, and let's go to the extreme. I'm gonna define uniform stability. Uniform stability. So for any data set S and any I and any zi prime. By the way, what I've written is for symmetric algorithms because this step requires symmetry. This is for symmetric algorithms. For non-symmetric, you can keep around this average if you wish. It's in case that the first data point is different from the second data point. Oh, the order matters, right? So I'm going to require that the G hat n of Z1 through Zn evaluated at Z minus G hat n evaluated at Z1 Zi prime Zn. So what's meant here is that any ith coordinate, take out the data point and put a replacement less than beta. So this is called a notion of uniform stability. Okay. So there are no expectations here. It's per sample and per coordinate that you're going to change and per replacement. And again, because of the symmetry, I think we can just talk about the first coordinate being replaced. This is the typical notion of uniform stability. Right. So in particular, you see that this can be upper bounded by beta, right? Because this is the expected version. This is really a much harder for any, not an expectation, but for any difference, right? So the more you ask for, the more things you can prove, essentially. So in particular, with this notion of stability, you can prove that not only an expectation is this small, but also with high probability, this difference is small. Right? So really, if you have this strong notion of uniform stability, your algorithm, whatever you see on the data, the empirical fit, that's what you're going to see out of sample. Okay? Now, of course, it's not clear if there are algorithms of this type, which are non-trivial, right? And moreover, we need to be minimizing empirical risk, right? Because otherwise, the generalization gap makes no sense, right? Because you're subtracting off a large quantity from what you want, right? The expected empirical risk. Any questions at this point? Okay, so I have 15 minutes to prove that the algorithm that Lorenzo introduced in the first few lectures, the regularized least squares, is actually uniformly stable. So that's another way to prove a gap on the performance of regularized least squares. Let me mention that I believe that until this point, it's not known whether one can achieve optimal results through this method. One has to do a different bias variance decomposition to get optimal rates if you care about these optimal rates. But this is a quick and dirty way of getting some result for regularized least squares in RKHS. Okay, so claim is that the f hat n, which is argmin over f of, I guess, h, 1 over n sum f of xi minus yi squared plus lambda norm of f squared in the RKHS space that corresponds to some kernel k, right? It's the regularized least squares. Is a something like 1 over lambda n uniformly stable. And there are a few assumptions, such as Lipschitzness of the loss function, which for a square loss implies boundedness. Right? This is only Lipschitz when f and y's are bounded. Right? So these are the assumptions that I'm not writing out, but they will come into the picture. Any questions? So let me explain why this is the case. Let me hand wave first. Imagine that this is not minimization over some infinite dimensional space, but instead a minimization over some RD, and that norm is the Euclidean norm squared. Okay. So what you have is a strongly convex objective because of this added regularizer. That objective pulls you towards 0. It's a strongly convex. It makes the objective function strongly convex. So think of it as rising quickly. Right? Now, when you perturb one data point in the data set, which is what we need to do, when you perturb one data point, that objective only changes here on the order of 1 over n. Right? So think of this as this bowl, and then it shifts a little bit for the new objective, and that's on the order of 1 over n. But of course, there is lambda, which is how strong the curvature is. And that governs how much the minimum moves. That strong convexity parameter tells you how much the minimum will move. And so essentially the bottom line is when you put everything together, that stability is going to be 1 over lambda n. Right? So for the next 10 minutes, I will make this more explicit. Let me just say whether this... well, okay, fine. Let's go on. All right. So suppose that you have a phi is sigma strongly convex. The definition is the following: phi of, and let's just work in RD. So I'm going to work with vectors. Phi of u is at least. So the function phi curves at least as phi of v plus gradient of phi u minus v, and plus sigma over 2 distance between u and v squared. And this is a Euclidean norm. Right? So that's the definition of strong convexity. The function rises at least as the first order approximation plus a quadratic. And whenever you have a convex function plus a quadratic, it implies that the function is at least lambda strongly convex, but maybe more. So suppose now you have phi and phi prime, which are strongly convex. Phi prime is the same, has the same definition. Yes. We need that f is of x is bounded. I don't think we're going to need that x itself is bounded, just the f of x. And because f is an element of RKHS, by representative theorem, you can always bound the value f of x by the region of the kernel, kxx. So that's the assumption that we're going to make. Okay, so you have this, and you have a phi of phi prime, u prime, phi of. I'm not going to write it down. So suppose that u prime, u and u prime are such that they're minimizers. Yeah? So the picture is that you have a strongly convex function and a slightly perturbed strongly convex function. This one is the minimizer, that's u, and this one is u prime. Right? So then I have a phi of u prime is at least phi of u, that's the minimizer, plus the gradient is 0. This is the gradient at u. Sorry, a gradient at v. Okay, so will this be confusing or not? I think it's okay. Plus a sigma over 2 distance between u and u prime squared. And then I also have that phi prime of u. So this is the suboptimal point with respect to phi prime, is at least phi prime of u prime, which is the minimizer, plus sigma over 2 u minus u prime squared. So when we combine these, you get that sigma times u minus u prime squared is upper bounded by, so bring things around, phi of u prime minus let's see, how do I want to combine them? So this is going to be phi prime of u prime plus phi prime of u minus phi of u. Okay, that's how I want to combine them. I mean, the point is that if these vertical distances are small, then the minima have to be close, right? There's no way you can have a curved function, a curved function like that, such that they're close at the minimizers, but these points are far away. It's just not possible because the function curves up quickly, right? That's all I'm saying. Okay, so now take phi prime to be the original data. So let's say we take phi to be so phi of f. Now I'm instead of u, I'm going to work with functions. So phi of f. Now you have to be careful because now we're working in the infinite dimensional space, but you can boil it down to working with the coefficients in the expansion, so everything is fine. So phi of f is going to be defined as 1 over n sum of f of xi minus yi squared plus lambda norm of f squared. And phi prime of f is going to be 1 over n sum, where x now is in the perturbed data set, where the ith coordinate has been perturbed. Okay, so this ith coordinate has been replaced with some zi prime. Okay, the ith coordinate has been replaced with zi prime, and let me write it like this: f of x minus y squared plus lambda norm of f squared. xy. Okay? So slightly different objective. Right? The minimizer of this objective is the f hat. The minimizer of this objective is the slightly perturbed f hat. And we want to understand the stability with respect to a change of one data point. Right? And you can already kind of see that because these things don't change too much, the minimizers are close, and therefore the resulting algorithm is stable, right? So RKHS has this regularized least squares in RKHS has this uniform stability. Okay? So you see phi of u prime minus phi prime of u prime. So it's just the difference of this objective and this objective at f prime. So it's difference of this objective and this objective at f prime. These terms cancel, and everything here cancels except for one loss. So the difference of so now we can write f hat minus f hat prime. So f hat prime is going to be the minimizer with the perturbed data set. Is that okay? I'm not going to write it down, but this is upper bounded by a loss of f hat prime at x. Okay, now I'm going to get lost in indices. So let me just copy this. Oh, and sigma becomes a 2 lambda because we didn't divide lambda by 2 there, so it's 2 lambda is the strong convexity parameter. It's upper bounded by at xi minus yi squared minus f hat at xi minus yi squared plus f hat of xi prime minus yi prime squared minus prime of xi prime yi prime squared. Okay. Now this is the RKHS norm. Yes. 2 lambda because this sigma is sigma over 2, but here I didn't divide by 2. No? Maybe you're right. Maybe there is no 2. Is there? I don't know. Up to factor of 2 is correct. Maybe I'm off a little bit. Okay, so the bottom line is that this is bounded by some constant c. Oh, and there's 1 over n. That's important. There's 1 over n, right? 1 over n was multiplying every single loss. So this is upper bounded by c times 1 over n times the L infinity between these two functions. So C has a bunch of constants which depend on the Lipschitzness of this, right? So I'm just using the a squared minus b squared upper bounded by a minus b equal a minus b times a plus b, and I'm getting rid of a plus b by absolute value. So that's all in here. You'll see it in the notes. But it's also true, as we were discussing just before, that the L infinity norm is upper bounded by so C times 1 over n, again by RKHS norm minus f prime. And it's okay if you don't understand this step. H with kappa, which is the ridge of the kernel. So because you're combining function, your f's are combinations of the kernels, they can't go higher than the ridge of the kernel, right? The ridge of the kernel being k of x comma x. If that is bounded, if you have a Gaussian kernel which goes up to 1, you cannot get any function that has values more than 1, right? Okay, so now we cancel the norm on both sides, and we get that the minimizers are close. So the minimizers now f hat minus f hat prime in the RKHS norm are bounded by C times 1 over n times kappa, and we divide by lambda n. Okay, so kappa over lambda n. And that's it, because now we plug it back in. The G, if the solutions f hats are stable in this very strong sense, then the losses, the G's are also, G hats are also stable. So you'll find the details in the notes. But I hope the kind of the basic idea is clear, right? It's just that this regularizer, the regularizer in the RKHS enforces stability, which is kind of interesting because the regularizer is often added for solving inverse problems for computational purposes. But here you can see that the stability, or the regularizer manifests itself as enabler of stability, which in turn gives you a generalization, or ensures generalization gap. So this was a line of work that Tommy was pursuing in the 2000s, the connection between stability and the generalization. This particular result that I'm describing here is due to Bousquet and Eliseev in 2002. The area kind of became quiet for 10 years maybe, and there was now a resurgence of stability-based analysis, also because of the differential privacy, trying to understand how various stability notions of the algorithm imply a bound on the generalization gap. Right. Okay?
Tell me, the compression analysis, I'm sure this is published?
Yeah, this is standard. Yeah. I will be giving a talk in 2 hours if you're interested on interpolation, some of the parts that you haven't seen in class, and you're well prepared and welcome to attend. I think it's going to be in Stata somewhere at 4:30.
Part of the homework.